So we are in the fifth lesson, that is laws of motion. In this, let us consider equilibrium of a particle. See here, let us consider some examples. On this body, two equal forces are working in opposite directions, so that the resultant force will be 0, and therefore the body will be under rest, and this is called equilibrium. And here also a block is placed on table surface. Upward is the normal reaction exerted by the table surface, and gravitational force downward. These two forces being equal in magnitude and in opposite direction, the net force has become 0. That's why the body is at rest. Similarly, here an object is suspended by a string from the floor. Here gravitational force on the body is mg working downward, and see, this gravitational force tries to stretch the string. Immediately inside the string, a force will be established to restore the string to its original position. That is, this restoring force in string is called tension, and it opposes the stretching of the string. Gravitational force tries to stretch the string, and the tension force opposes the stretching. Anyhow, these two are equal in magnitude and in opposite direction, so the net force is 0. So in all the three examples, so two forces are working in a line, and they are equal in magnitude and in opposite direction. This minus sign indicates that they are oppositely directed, and then the object is under equilibrium. Now let us consider another example in which three forces are working. Two frictionless pulleys are there. Over the pulleys, string is taken, the two strings tied here and another string tied to this. Here at the end of the three strings, slotted weights are attached. The weights are so adjusted that the point P is under equilibrium. Now the gravitational force on this be F1, on this F2, and on this F3. This gravitational force on this body will be pulling this point in this direction, and gravitational force F2 will be pulling the point P in this direction. This is F1, this is F2, and this force is pulling the point P in this direction. So on point P, three forces are working. This is F1, F2, F3, and this point is P. All the three forces are working along the same point. That's why the forces are called concurrent forces. Concurrent forces. Now, Let us determine the condition. See here, by adjusting the weights here, we adjust the weights such that the point P becomes under equilibrium, or it will be under rest. Until it achieves equilibrium, we change the masses here. Now the point P is at rest, the point P is under equilibrium. So now we can take the shadows, the shadows of the strings on a piece of paper, and based on the masses we choose the lengths, and suppose we got such diagram. Now what we do here, suppose here 100 grams mass is there, here 100 grams mass is there, here 150 grams mass is there. We choose a scale like this. 50 grams is equal to 1 centimeter. So for 100 grams here you get 2 centimeters. Here for 100 grams you get 2 centimeters. And here for 150 grams you get 3 centimeters. So like this. Now afterwards we draw a parallelogram. Parallel to this side we draw a line here, and parallel to this side we draw another line here. The two lines intersect here, and this is the diagonal for the parallelogram. If this is F1, this also F1. Vector sum of F2 and F1 is given by this vector. So this stands for vector sum of these two vectors. Now this can be taken like this. This is P. Here F1 plus F2. Here F3. Now two forces are in a line, and since it is at rest, sum of upward forces must be equal to sum of downward forces. So we write an equation. This is vector equation. Therefore we put a negative sign here. This tells that this and this are oppositely directed. Now we also can write this as is equal to 0. So this is the required condition for the point P to be under equilibrium. A vector can be expressed in terms of its xyz components like this. If this is F1, for F2, for F3, adding all the three vectors. Adding all the three vectors we get F1 plus F2 plus F3 is equal to, here all these are I coefficients and x components, summation of x components I, these are y components, summation of y components j, summation of z components k is equal to 0. And this equation can be equal to 0 only when the sum of x components becomes 0, sum of y components is equal to 0, and sum of z components is equal to 0. So this concept is used while solving the problems. So there is another way. Suppose the three forces are drawn again here, F1, F2 and F3. This is point P. Now suppose this F1 is drawn here, F1 is drawn here in the same direction, same magnitude, and here F2, same direction, same magnitude. Now F3, this is F1, this is F2, this is F3. See, the vectors, the three force vectors working on P, if you can express these vectors as three sides of a triangle, then you can say the point will be under equilibrium. There should be no gap. So this is another way. This is called a triangle law of vectors. What if there are four vectors? If four force vectors are working on a point, these are also concurrent forces, all the four forces working through same point. See here, this is the F1 shown here, F2 here, F3 here and F4 here. So all the four forces could be, these four forces could form a closed figure, a quadrilateral. Therefore, the point O will be under equilibrium. If there are five forces, if the five forces could form a pentagon, then the point will be under equilibrium. Just like that, six forces hexagon. If there are n number of forces, we get a closed figure, n-sided polygon. If you get, then the point will be under equilibrium. Now let us do a problem, a solved example. .6. In this problem, from ceiling to a 2 meter length string, 6 kg mass is attached, and at the middle point, horizontal force is applied. On this, see, gravitational force is mg, mass into g value, see 6 kg into g value 10, if you take 60 newtons, force will be working here. See, when we already know the gravitational force tries to stretch the string downward. Immediately a force is produced inside the string that opposes the pulling force, that opposes the stretching force, and that is called tension, restoring force inside the string. Under equilibrium, these two forces will be equal in magnitude and opposite in direction. So here, to oppose the stretching of the string by this force, here tension is produced inside the string, say that is T1. And under the action of these two forces, here also the string will undergo stretching, and that stretching is countered by the tension force, say that is T2. Now when the horizontal force is applied here, the vertical string becomes inclined, here like this, 60 newtons, 50 newtons, here T1 tension, here T2 tension. This is the point P. Let us draw this line extended upward. See, this string is making angle theta with the vertical line, and this angle theta is asked. To find the angle theta, let us divide this figure into two free body diagrams. First, let us take this free body diagram 1. On 6 kg mass, downward 60 newtons, upward T1. And this is under equilibrium, therefore T1 is equal to 60 newtons. Now let us take another free body diagram. Here T2, here horizontal force 50 newtons. Now see here, according to Newton's third law, forces appear in pairs. T1 on this body is upward and T1 on the point P will be downward. And there is another way also, we can, using our common sense, we can decide T1 here. Gravitational force is trying to stretch the string, increasing its length. Tension in the string opposes the stretching. So you can see the two arrow marks opposing the stretching of the string. Okay. This is T1. This is theta. Now extend 50 newtons backward. Now the T2 force can be resolved. See here, T1 equals 60 newtons. Okay. Let us resolve this vector into two perpendicular components, one along y-axis, another along x-axis. This side is adjacent to theta. Therefore, if this is T2, this will be T2 cos theta. This side is opposite to theta, therefore sine comes. If this is T2, this will be T2 sin theta. If this is T2 sin theta, this also T2 sin theta. Now T2 cos theta is equal to 60 newtons. And T2 sin theta is equal to 50 newtons. First equation divided by second equation. T2 gets cancelled. Sin theta by cos theta is equal to tan theta. 5 by 6. Or theta is equal to tan inverse 5 by 6. So in this way we determine the angle theta.